Similar figures. Let's start off with definition. Similar figures have the same shape, but not necessarily the same size. It's like it's like an architect who draws a building and then builds it. The drawing is not the same size as the building, but they're proportional. So since they're figures, they're called similar figures. Two triangles are similar if the ratios of the lengths of corresponding sides are equivalent, and the corresponding angles have equivalent measures. Angles that have equal measures are called congruent angles. So let's look at these similar polygons, triangles. For two polygons to be similar, corresponding angles must be congruent. So if you see angle A is congruent to angle E, 43 degrees. Angle B is congruent to angle F, 47 degrees. Angle C and angle G are congruent. Those are right angles, 90 degrees. The corresponding sides must have lengths that form equivalent ratios as well. So A to B is 60, E to F is 30. And when you put 60 over 30, you get 2 over 1, which we're going to walk through this process in just a second. But just know that the corresponding angles like AB over EF, BC over FG, AC over EG, those simplified ratios all need to be equivalent. Here's your first example. The question is, which rectangles are similar? The first thing you need to notice is that since all three figures are all rectangles, all the angles are right angles. So the corresponding angles are congruent. But remember, in order for a figure to be similar, it's not just that the angles are congruent, it's also that the corresponding sides are equivalent ratios. So we're going to continue to try to make sure that these are similar. Compare the ratios of corresponding sides to see if they are equal. So the length of rectangle J over the length of rectangle K. So you see J, K, 10 over 5, and we're going to put 4 over 2 because those are corresponding. Long side over long side, short side over short side. So let me show you that again. Long side over long side, length over length, 10 over 5, width over width, 4 over 2. Are they equivalent ratios? Cross products. See the cross products of these ratios. 5 times 4 is 20. 10 times 2 is 20. So yeah, these are equivalent ratios. Now, we've got to check the other ones, though, because there are 3 figures. So we can take 10 over 12 and 4 over 5. 10 over long side over the long side. This time we're comparing J and L. 10 over 12, 4 over 5. 10 over 12, 4 over 5. Are they equivalent? 12 times 4 is 50. 48, sorry. 5 times 10 is 50. So 50 is not equivalent to 48. Those are not equivalent. So no, those 3 triangles are not all proportional to one another. So you try. Which rectangles are similar here? First, compare A and B. Compare B and C. Compare A and C. Figure out if these are which of these rectangles are similar. Press pause and try it. So the 3 figures are all rectangles. All the angles are right. So the corresponding angles are congruent. We can check that off the list. Now let's look at the sides. So hopefully, let's see, 8 over 6 and 4 over 3, that's A and B. So 8 over 6, 4 over 3. 6 times 4 is 24. 8 times 3 is 24. Oh, rectangles A and B are congruent. They're similar. Let's try A and C. 8 over 5. 8 to 5 equals 4 to 2. Let's find out. 8 times 2 is 16. 5 times 4 is 20. So no, rectangle A to C is not similar. A to B was. So now we're going to talk about scale factor, the ratio formed by the corresponding sides is the scale factor. Remember when you blow something up and you use scale factor, dilate? If you dilate by 2, you multiply everything by 2. If you dilate by half, you multiply everything by half. Well, now you need to know that the ratio that was formed is the scale factor. So, for instance, on this one, 8 to 6, 4 to 3. 4 to 3 is the reduced ratio, so 4 to 3 is the scale factor. Now, so we're going to take a look at this example to walk through similar figures with scale factors. So what we're trying to do is figure out how much was it blown up by, or how much was it reduced by. So that's what we're going to be working on now. A picture 10 inches tall and 14 inches wide is to be scaled to 1.5 inches tall to be displayed on a web page. So we're going to shrink this picture so we can put it on a web page. How wide should the picture be on the web page for the two pictures to be similar? So this is pretty important, because if you don't make the width proportional to the how tall it is, then that picture is going to look distorted. It's going to be all stretched out. So we want to make sure we do this just right. First thing we're going to do is set up the heights over the heights and the widths over the widths. So we start, the original is 10 tall, 14 wide, and we put those over 1.5 tall, and we don't know how wide. We're trying to figure that out. Cross products, we're going to do XMed. Cross multiply, which we just did. 10 times x is 10x. 1.5 times 14 is 21. Get the equation. 10x equals 21. Inverse operations, division. Divide by 10. And we're going to come off to the side and do this math to bring the decimal straight up. 10 goes into 21 2 times. 2 times 10 is 20. 21 minus 20 is 1. So we could write it as 2 1/10, remainder over divisor. Or we can add a 0, bring it down. 10 goes into 10 one time. 10 times 10 is 10. 10 times 1 is 10. 10 minus 10 is 0. So we could also write it as, read it, 2 1/10, or 2 1/10. You can write it as a fraction or a decimal is what I'm trying to get at. So this, in order for the two pictures to be similar, then the one on the web page needs to be 2.1 inches wide. So here's another example. There's a little bit of dimensional analysis in here. So let's see if you catch on to that. Press pause and try this one. Okay, so a toy replica of a tree is 9 inches tall. What is the length of the tree branch if a 6-foot tall tree has a branch that is 60 inches long? So what we have here is we got a toy, and then we have the tree. So the toy is 9 inches tall, whereas the tree is 6 feet tall. And the toy, we don't know the length of the branch, but the big tree, we know that the branch is 60 inches long. What I have right here is a whole bunch of inches and 1 foot. So we're probably going to want to change that foot to inches because you need all the units the same. So you write down what you're going to use. 1 feet equals 12 inches. That's our conversion. We're going to take 9 inches over 6 feet and multiply by the conversion factor. 1 foot is 12 inches. Remember, you want the feet to be diagonal from one another because that's what you want to get rid of. Now we've got inches and we can multiply straight across. 9 times 1 is 9. 6 times 12 is 72. So I rewrite my proportion with all the inches. So 9 inches tall, instead of 6 feet, it's 72 inches tall. X inches long, because we don't know how long the toy is going to be, the branches on the toy, to 60 inches long, which is the big tree. Cross multiply. 72 times x is 72x. 9 times 60 is 540. Write down that equation. 540 equals 72x. Inverse operations, divide by 72. And that gets rid of the 72's. and the toy replica, the branches are going to have to be 7.5 inches long in order for those to be similar. So your scale factors are the reduced ratios. So the 9/72 can be reduced to 1/8. So you could also say that the scale factor is 1/8, which we did whenever we did scale factor. So this is how you take your dimensions and try to find the missing dimension. Make sure that you do cross multiplication to get your equation, and you write down the equation. Make sure your units are the same. Sometimes you have to use conversion factors, which is fine. It's an extra step that's just off to the side. So make sure you get all this written, and good luck.